Okay. We have Paul Robertson joining us from the University of California, Irvine today to talk about the challenges and rewards of EPRV studies of M dwarfs. So, Paul, take it away when you are ready.
All right, thanks, and good morning or good evening, wherever you are. Consider this talk a bit of a stump speech, I guess. So I wanted to remind folks that not all stars are sun-like. There's been a lot of talk in the community lately about the sun specifically, not just sun-like stars, and I think that's quite appropriate. A lot of the challenges that we're dealing with at the forefront of EPRV can best be addressed with the solar feeds on these spectrometers. But that's not representative of the majority of the galaxy. We see graphics like this that show the stellar sequence and the actual space on the slide is dominated by stars like the sun and hotter, but the vast majority of the galaxy's stellar population, and in fact, the stellar population of the solar neighborhood, are dominated by these small, cool M dwarfs. And so maybe a better visual representation is this little animation of the 10 parsec solar neighborhood. And these stars are color coded by the temperature of the star. And so you can see a lot better that we're really, dominated by this cool red population. The numbers on this plot are now out of date because this plot was made earlier than this morning. It's the number of planets known around each star. We still have nine for the solar system, which I think is either retrospective or forward-looking. I don't know which. Um, but I like to show this, and my intro astronomy students always get a kick out of the fact that despite this proximity, of course, none of these M dwarfs are visible to the unaided eye, except maybe when they have super flares briefly. Um, so there are a couple of aspects of this. One, if you want to understand the galactic exoplanet population, you need to start with M dwarfs. This is the dominant stellar system. It's the dominant planet formation process. It's potentially the most common type of habitable environment in the galaxy. And it may not look like what we have here on Earth, but potentially hospitable to some forms of life. There are also some distinct observational advantages of working with M dwarfs. And this part may be familiar to a lot of you, but I'm showing here the Doppler amplitude of various types of planets. And of course, highlighting the ones that we're most excited about, the Earth mass planets in the habitable zone. So this has to do with the fact that the planet to star size ratio is so much larger for an M dwarf. And so the gravitational reflex motion is going to be higher, but also the planet is closer in. And so that further increases the Doppler amplitude, but also makes the orbital period shorter. And so you get a full order of magnitude increase in the amplitude that you're looking for, but you can also potentially cover a full period in a single observing season or less. And so that, in multiple ways, places less demand on your instrumental stability because you still need really good night-to-night stability, potentially extreme precision for some of the planets that I'll highlight later in this talk. But if you have a 0 point offset between observing seasons, that doesn't end the ball game like it would for a planet in a 1 year orbit, like we're trying to get with sun-like stars. This extends to signal amplitudes for transiting planets. Because this depends on the radius ratio squared, you get a significant increase in transit depth for, again, that habitable zone Earth. And you also get a factor of two in geometric transit probability because, again, the habitable zone planets are so much closer. And so there are a number of science cases that either rely on or are enhanced by the ability to go after M dwarf planets, or and one of those is simply the ability right now to characterize Earth or potentially sub-Earth sized planets. And so one of the places we're seeing this really start to emerge in large numbers is in filling in the mass radius diagram for transiting exoplanets. And I show here the plot from Luque and Paillet of a very well characterized set of M dwarfs where we see this potential dichotomy on the mass radius diagram, and this is pointing towards a number of really interesting questions that we can potentially answer specifically by looking at M dwarf planets. Things like what are the formation and migration pathways, if there is a distinct population of water worlds, as you see on the upper um, uh, curve here. That's potentially suggesting that these planets are forming in a water-rich region of the disk and migrating inward. Um, it also allows us to pin down occurrence rates as a function of stellar mass. Right now, our population statistics for Earth-sized planets and smaller are still small number statistics and dominated by a small number of systems. And so the ability to potentially discover more such planets, potentially blind with radial velocities, is another advantage. And of course, again, talking about habitability, a key question right now for M dwarf science is whether these habitable zone planets actually retain atmospheres when they're huddled so close to the star with all the intensive flaring activity that young M dwarfs undergo. And so, if we want to look specifically at transiting planets, of course, your signal and noise for atmosphere detection is also larger for M dwarf stars. So, this is a really neat set of simulations where we just take Earth and place it around a bunch of nearby stars and look at this is showing the number of transits required to get a 5 sigma detection of various molecules. So you can see at the bottom the color coding for those molecules. Um, and it's as a function of distant, we're taking these stars and placing them at arbitrary distances. And you can see that the M dwarfs are where uh, that we can really start to detect these molecules in a reasonable number of transits with James Webb. Um, and if only those Proxima planets would transit. But in any case, um, if we are going to have conversations like we've seen in the literature recently about biosignatures on small planets with James Webb, then M dwarfs are going to be our best bet for that. I'm not making any evaluations of what's in the literature so far, but even having this conversation is a lot more feasible for M dwarfs. And then finally, the last science case I wanted to highlight is just for direct detection rather than transmission spectroscopy. So yes, it is potentially helpful that the habitable zones are so close for these stars. It makes it easier to detect the planets in the first place. But then actually achieving the angular resolution to image them is going to be challenging if we have something like a 6 meter mirror on a space-based imaging campaign. So this is really where the ground-based 30-meter class telescopes are going to shine. Um, and transits are maybe not going to get us there. So um, if we're talking about a transit probability of 1%, there are roughly 300 M dwarfs in the 10 parsec solar neighborhood. You're only going to get a few candidates out of that. And so we need these blind RV surveys to potentially detect candidates for imaging like this. And for now, I'm going to leave this as a teaser, and I'll come back to in the results section. And so what I'm thinking of as kind of the mission statement here is that there really are some um, distinct advantages potentially for M dwarf planets, and taking advantage of that is really important for some exciting science cases on things like James Webb and the 30-meter telescopes. But actually realizing those advantages requires us to embrace the fact that these are not solar type stars and understand and account for their specific idiosyncrasies when we're observing them. And so with that, I'll start by flashing up some M dwarf spectra. Um, Again, this is going to be a review for most folks, but they are intrinsically faint. So notice the y-axis on this plot. These stars are getting exponentially fainter as they get cooler. And the black body peak is obviously shifting towards the infrared. And so we're going to have to work with infrared light, and we're also going to have to deal with the challenge of molecular line blanketing. So these stars' atmospheres are so cool that molecules are forming, and this will basically completely wipe out the continuum, particularly in the blue. And so we're going to have to think carefully about certain aspects of our data analysis there. And so one way to tackle this problem is to use infrared spectroscopy. And this is something that there have been big advancements, and I guess I'm giving a little bit of a preview for the next colloquium in this series. But I'll use the instrument that I've been a part of developing as a template here. So I'm part of the team that developed and is using the habitable zone planet finder on the Hobby-Eberly telescope at McDonald Observatory. This is a near-infrared, high-resolution, stabilized spectrograph, and it's leveraging the combination of infrared wavelength coverage and a large aperture, and so that's helping us simultaneously overcome the challenge that M-dwarf spectra are faint and infrared. And we've been able to get down to about a meter per second long-term stability with this instrument. And that might not sound like cutting edge to you if you've been following the progress of something like HARPS over the last 10 or 15 years. It's been done, but it's been done in the optical. And so I want to just kind of highlight here some of the challenges that have to be overcome in order to get stable on-sky RVs with an infrared instrument. So one thing you need is a calibrator. So we have a near-infrared laser frequency comb that was developed by our colleagues at NIST. Um, I remember when I was a junior grad student, we were talking about trying to do this with an absorption cell calibrator. And one of the better gases for providing lines in the near infrared was hydrogen fluoride, which is not a good idea in an observatory environment. And so we're fortunate here to have a laser frequency comb that has been remarkably reliable. Anybody who's worked with an LFC on a spectrometer knows that that's a real challenge. But this gives us good, reliable coverage across the whole bandpass of the instrument. The entire instrument has to be maintained in a stabilized, I would say, partial cryo environment. So we hold our instrument, our optical train, at about 180 Kelvin, which is designed to knock down the thermal background up to the detector's 1.3 micron cutoff. So depending on what your detector's wavelength sensitivity is, you might have to go colder. But this cooling and stabilizing of a cryogenic system across the volume of an instrument that's roughly the size of an SUV adds a lot of complexity and cost. Um, and when I first called Lakeshore to ask if they had temperature monitoring equipment that would do this, they literally laughed at me. So we've made a lot of advances there. And finally, like I said, we can't use CCDs for this. They're not sensitive at infrared wavelengths. So you have to use the H2RGs or H4RGs. And this requires, there are a lot of unique challenges with these devices. So um, they have issues with persistence and flux dependent responses and all kinds of other properties that CCDs just don't have. And so you need a really thorough data reduction setup, and you also need um, good hardware and software to actually control these devices in the field. So we have that with HPF. Joe Neenan's published some really valuable stuff on that. So what does this all look like rolled up? This is, and I think this is just the most recent time series of Barnard star that's been published from HPF. So this is stability at around 2 meters per second over years, and that's with no correction. So I haven't modeled any stellar variability, any planets, and we know now that both of those are present in this time series. Um, so this is showing we can, limited by astrophysics, get down to something like a meter per second on a quiet star. Um, and again, with the M dwarf advantage, this is sufficient to potentially detect Earth mass planets in the habitable zones of some of these nearby stars. And I don't need to spend too much time on this since Etienne is going to talk about this next month, but there is now a whole fleet of infrared Doppler spectrometers on sky. I'm highlighting a few of them here. Um, and I was going to call this slide Flat Lines on Barnard's Star, but the recent NERPS publication highlighted Proxima instead. And so we're seeing a flat line in the residuals around the planetary system there. Um, and these are not all copies of each other. So some of them have adaptive optics, some of them have different wave bands, so it's more or less infrared. Um, and Yeah, Spiru has polarimetry, so there are a lot of interesting features that potentially help us either get better precision in the infrared or better understand the stellar variability of our targets. I'll show here a plot estimating the Doppler information content of these M dwarf stars as a function of wavelength and temperature. And the reason I'm showing this is to highlight M dwarfs are information rich overall because they have so many lines. But I'm also highlighting you don't necessarily have to go fully infrared in order to leverage the maximal information content potentially. Especially for the early to mid M's, you can get a lot or most of the information content you need in the kind of red optical 700 nanometers out to a micron. And so you can potentially do this with a CCD device, not introducing all of the challenges of an infrared spectrometer. And so I'll highlight here a few of the instruments that are taking advantage of this. Carmenes actually has two channels, so there's an optical and an infrared arm. But you can see in the blue there that the optical arm actually extends into that red optical, and so you can do really well on early to mid M's just with that arm. Likewise, NUID and Maroon X both extend well past 900 nanometers, and so these work well on sun-like stars and M dwarfs. And I'll point out in particular, there's kind of a sweet spot at the mid-M where both the optical and the infrared instruments get really good precision. And so I'll highlight at the end some of the systems that we've been able to study with both of those and get some of the unique advantages of both and make some really interesting detections. Um, Once you have a fantastic spectrometer, it's not all hardware, and extracting good RVs from these instruments can be a challenge. So the standard technique that you'll see in a lot of um, built-in pipelines that observatories host, and you just go download your RVs the morning after the data are taken, use the cross correlation technique to produce RVs, and that's what I'm showing here. So you cross correlate your observed spectrum with a mask of lines where you expect lines to be at that spectral type, and you get essentially a super sampled average stellar line, and you can determine the velocity position of that line, and that's your RV measurement. Because of the line blends, that doesn't work well for M dwarfs, and if you look at the masks that are being used for your M dwarf spectra, say on the NUID archive, you'll see that we don't even have masks past M2. And so there are a number of alternative approaches that work better for M dwarfs, and these have been shown to work really well. In particular, the template matching approach, which I'm showing here, you take all of your stellar observations of a target and you combine them to make a template of the star. And then you determine the shift between the template and an individual observation to determine what the velocity shift must be. And that works a lot better for M dwarfs. It leverages the full wavelength span of your data and can get to much better precision, again, than what you might see on a default pipeline run of an M dwarf. Another approach that works really well is the line by line method, where you get an individual velocity for each line, and you can see the uncertainties on single lines can be kilometers per second, but root n statistics are powerful, and you can average down to something that is equivalent or potentially better than what you get with something like a template matching technique. You can also filter out bad lines where bad means detector artifacts, tellurics, activity sensitivity, however you define it. One interesting result here is that unlike with the CCF technique, it it doesn't matter so much that we don't have individual absorption lines. This is an example from Spiru showing a line here is defined as any span between two maxima in the spectra. And that works really well. So maybe we don't have to worry too much about what is a line for an M dwarf. I'll show here, and this is really just to kind of point out that I'm skipping over a whole field of literature because I don't have time. But extracting RVs is not the only challenge when getting data products from your M dwarf spectra. If you want to look at some of these activity sensitive features in the spectra, those are also different for M dwarfs. And so one of the things that jumps out immediately is the continuum blanketing from molecular bandheads. And so if you're normalizing to the continuum, you need to think carefully about that. If you're using some of the canonical activity tracers like calcium H and K, the continuum there can be so weak that your activity tracer just becomes dominated by signal and noise. Line blending is obviously a problem. So a lot to think about. I'm highlighting here the near-infrared potassium 1 feature that's been shown by Tarian et al. To trace, in particular, variability caused by Zeeman splitting, which seems like it might be a dominant factor, particularly in these quiet, slowly rotating M dwarfs. Um, so again, just kind of pointing out that this is another thing that has to be treated, especially for M dwarfs, depending on your spectral type, your instrumental waveband, etc. But it does segue into kind of the next problem. Like, okay, suppose I have a fantastic red optical or infrared spectrograph and I'm extracting my data perfectly. Of course, this is one thing that doesn't change from sun-like stars. Uh, our sensitivity is going to be limited by stellar variability. And this animation where we have a dark spot rotating on the stellar face is perhaps an oversimplification, but it does highlight an important aspect, which is that a lot of the variability that we're going to be chiefly concerned with is tied to the stellar rotation. And so understanding the stellar rotation and everything that comes along with it is important. But again, I'm concerned that these stars are not sufficiently sun-like for us to just use the sun as a template to deal with this. And so this is showing for various types of stars how energy moves from the core where fusion is occurring outwards to the atmosphere. And again, it's a little oversimplified. We believe that these M dwarfs become fully convective at about 35% of the solar mass. But that's a lot of the stars that we're talking about today. And so there are changes that come into place when a star becomes fully convective, namely that you don't have the boundary between radiative and convective layers, which is known as the tachocline. And this has been theorized to be the origin, the dynamo that drives the global magnetic field on the sun. And so if that isn't present for M dwarfs, then it's not obvious that the stellar variability will originate from the same mechanisms or behave in the same way. With that said, there have been some really interesting um, recent observational results that suggest that even if M dwarfs are lacking a tachocline, they have a lot of the same magnetic behaviors. And so this is an example showing the X-ray luminosity, which is sensitive to magnetic field strength, as a function of the Rossby number, which is just the ratio of the rotation period to the convective turnover time. There are some results that suggest that you can just use rotation period, and that works fine. Um, but this is essentially showing us that stellar magnetic activity for M dwarfs, which are here color coded with red points, FGK stars are in gray. Um, it's connected to stellar rotation. So you, at some point, rapid rotation, you saturate, and then it drops off as the stellar rotation slows. And you can see this for various activity tracers. I know H alpha luminosity is another one. Um, so the fact that you can plot the M dwarfs and the sun-like stars on the exact same plot and they follow the same lines um, is indicative of something. I'm not sure exactly what yet. Another example is the discovery of long-term magnetic cycles for fully convective M dwarfs. So I'm showing here the 7-year cycle for Proxima Centauri. There have been other fully convective stars that have shown this. I'm just showing the one that we all know. Again, these magnetic cycles are believed to be connected to evolution of global magnetic fields caused by shearing at the tachocline. And so what these results are showing is one of two things. Either you can get the same magnetic behaviors, and those behaviors are connected to rotation. You can get those without a tachocline, or these magnetic fields and their behaviors are being generated in the convective layers independently of a tachocline for all of these stars. And I don't think we know which yet. So looking more deeply at M dwarf rotation, um, if you ask me to say, how do M dwarfs rotate, it's either really fast or really slow. And so this is looking at a few dimensions of the problem for a collection of measured stellar rotation periods. Basically, what you can see is that they cluster either around very rapid rotation, or there's a track for slower rotators. And there's a noticeable gap in between, which seems to indicate that stars begin their lives rotating very rapidly. At some point, there's a type of phase change where they move from the rapid rotator track to the slow rotator track, and that happens fairly quickly. This does mean that there's a population of M dwarfs that rotate very slowly, and these can be really fantastic targets. They're slow rotators. They tend to be pretty quiet in their activity behaviors, and so these can be great RV targets. There's still going to be variability that we have to deal with, but it's less, and it's also evolving slowly enough. The best example of this is Proxima Centauri, 80-day rotation period. You can hammer it over a short period of time, and the short period planets appear with the stellar rotation just looking like a long-term trend. Of course, there are challenges associated with this, as you can see there from the rapid rotator track, especially as you go towards later spectral types, a larger fraction of those stars remain on the rapid rotator track. It seems that magnetic braking potentially is not as effective for those. And so you see more stars retain rapid rotation. This can lead to higher activity levels, larger levels of jitter, but also high V sin I. So this is a cumulative distribution plot of V sin I for various stellar populations. And this leads to a permanent degradation of the RV precision you can achieve. Um, You can overcome some of it with higher instrumental resolution, but there's a definitive cap on that. Another challenge for the slow rotators is that those rotation periods and their aliases and harmonics uh, tend to overlap with the period space for habitable zone planets, especially for early and mid-type Ms. So um, those habitable zone periods, I would say, are between maybe 30 and 80 days. So if you have stellar rotation periods between, say, 50 and 100 days, then you can just about guarantee that the rotation period or its first harmonic is going to overlap nicely with the habitable zone. And there have been some studies that show that even with smart activity mitigation, you get a permanent loss of signal detection power when you're near the stellar rotation period. Of course, this does get better for the latest spectral types. Again, Proxima is a great example. The rotation period is at 80 something days, and the planetary system, including the habitable zone, is at 11 days in interior. So that gives you a nice amount of separation in frequency space where the disentangling isn't going to be as challenging. These long rotation periods can be really difficult though because they last a long time and the spot lifetimes can be pretty long. So if you have 100, 150-day rotation periods, Barnard star is about 145 days, so it's getting really long. It's comparable to the duration of a single observing season, and that tends to exacerbate aliasing. If you have a rotation period that matches an observing season and it's changing phases between seasons, then that can, if you look at a power spectrum, it spreads the power of the rotation period out into a cone like this. So these are all peaks associated with the stellar rotation period. It's not clear what the actual period is. And obviously, you've got power spilling out into a lot of places that you might be interested in finding planets. This is an insidious case with Barnard star where the 145-day rotation period, um, depending on the season you observe it, will often appear primarily at the 1 year alias of 230 something days, which led to a false positive planet detection. There's a lot of plots here. I'll highlight the middle, which is where the signal appears most strongly in radial velocities. You can see that peak is actually matched in the calcium H and K index, where only the H alpha is showing the true rotation period. So, not to terrify everybody too much with stellar rotation periods, um, I will highlight one potential place where stellar rotation might help us. This is with the ultra-fast rotators. So this is a population of stars that have rotation periods less than a day. It's a distinct cluster. I don't know if people can see my cursors, but this is here rotation periods from Kepler in pink, TESS in blue. There's a distinct cluster of M dwarfs that have this very rapid rotation. And this is interesting because if you study the rotation of an individual object, you see that the spots or spot complexes will often last significantly longer than what we observe for sun-like stars, where the spots evolve within one or two stellar rotations. This is a stacked phase curve of an ultra-fast rotator that has a 6 hour period. And the way to read this plot is from bottom to top is 1 week of the stellar rotation, and then we move forward a week at a time from left to right. And so you can see over an entire, actually many test sectors, the bright and dark phases of the rotation curve are not evolving. And this is for a 6 hour rotation period. This is hundreds or thousands of stellar rotations where the spot behavior is not evolving. And so if we translate this to radial velocities, these are HPFRVs of another ultra-fast rotator that has about a half-day rotation period. And I've done nothing smart here. There's no GP modeling, there's no wavelength space correction. I have fit a sine curve to a rotation signal of 100 meters per second amplitude, and I get residuals that are down approximately at photon noise for this target. So this is more than a 90% reduction in stellar variability. And it leads me to speculate that perhaps we could use the fact that these stars are so reliably active to simplify our activity corrections and actually look for planets around these stars. And so this is a survey that we're starting called Surveying Ultrafast Rotators for Super Young Planets, or SURFs Up. I'll go over this quickly because I'm running short on time. But basically, we've done a reconnaissance survey of these ultrafast rotators to try to find the ones where V sin I is not so high that we can't do RVs. But we're doing a proof of concept RV study on that target I just showed. The data will start flowing when the star rises next month, and maybe next time I talk to you all, I'll have some results to show. The last thing I wanted to highlight for M dwarfs is chromaticity. So, like I said, some of these targets are going to fall in the sweet spot where we can do really great RV precision in the optical and the infrared. And this can potentially help us discriminate between planetary signals, which should be achromatic, and stellar signals, which may not be. And so I'm showing here a great example of AD Leo, which is a highly active M dwarf. It has about a couple days rotation period, so it's not an ultra fast rotator, but still sometimes we'll have phases of extended spot lifetimes, which again led to a false positive exoplanet detection. When you look at it in optical, here in purple from Sophie and Spiru in the infrared, you can see a distinct amplitude difference, which is betraying the fact that this is a stellar signal. And so this has long been predicted due to the expected difference in spot photosphere contrast in the optical and the infrared. And it works most of the time. But I will caution you that this will not always be the case. So this is an ultra-fast rotator that we observed with HPF and Keck high res. This was so much fun because we could do this in high res on a night. We just sit on the star, we cover a full stellar rotation. Um, but you can see here that as far as we can tell to measurement precision, there's no difference in amplitude for this stellar rotation signal. And so if you're relying entirely on chromaticity to tell you the difference, you might be in trouble. This seems to have something to do with the per line contrast between a spot and the photosphere. This is a result that was discussed at the EPRV meeting this summer. And I don't think those talks are available yet, but I encourage you to check it out. This is showing using model spectra what the expected contrast is on a line by line basis for another active star, EV LAC. And you can see overall, yes, the contrast is different in the optical and infrared. There's a higher contrast in the optical, but for certain lines, even the infrared has high contrast. And so, yes, we can, appreciate this on the back end, um, but in order to predict whether we'll get the contrast advantage for an individual star, we would have to know both the spot geometry and temperature, and then we would have to know what that spot spectrum looks like. Do we know? Can we predict what an M dwarf spot spectrum looks like? My prediction is no, and I'll leave it with that. I'm running out of time. I'm just going to get to my punchline, which is that there has been a lot of progress made on all of these fronts, understanding the stellar astrophysics, and adapting our instrumentation, our data analysis, our survey strategy to take advantage of these. And the discoveries that are being made are really incredible. So I'll come back to Proxima Centauri. Um, Again, the orbital periods are short, but over years we do have to account for the stellar variability. When we do that, we get small planets in and around the habitable zone. The newest one has a minimum mass of just a quarter of an Earth mass. I think that's incredible. More recently, we saw a multi-planet system detected around Barnard star. So this is just showing the stellar variability that we have to deal with. If we account for that properly, we see now four small planets, sub-Earth mass. The smallest of these has a Doppler amplitude of just 22 centimeters per second. This is the smallest Doppler amplitude that's ever been detected blind. And I think I mean, we're within a factor of two here of the amplitude of an Earth around the sun. So this is showing we are really at the cutting edge. I'll leave you with one more. This is one that my former grad student, Corey Beard, has been working on for 5 years, and we finally got this under review. This is a chromatic Gaussian process analysis, again, using a combination of optical and infrared instruments to look at a nearby star, Gliese 251, which is the 46th or 47th closest star to Earth. It had a previously discovered planet that was first published by the Carmenez team at 14 days. When we put those data together with velocities from HPF and NUID, we see a second planet at about 54 days with an amplitude of just about a meter per second, which translates to a planet with a minimum mass of just under 4 Earth masses, and it's right in the middle of the habitable zone. And this is exciting because, as I said at the top of the hour, we're looking for planets that are potentially accessible to 30-meter class telescopes for imaging. This plot is showing where that planet falls in angular separation space, and this is showing for a hypothetical TMT imager. The lower band here is showing what the inner working angle might be. The upper curve is showing a somewhat arbitrary cutoff at 10 to the minus 8 contrast. And we can see that the entire habitable zone of this system is within those bands, and I think it's potentially a really exciting target for direct imaging. So I've gone a little long. I will leave my conclusions up and take questions. Thank you.
Okay, thank you, Paul, for an excellent talk and overview of where we stand with EPRV efforts for M dwarfs. Many clapping hands emojis, so clearly people were excited about your presentation. Questions for Paul? Please feel free to use the raise hand feature in Zoom, and then I will call on folks. One thing I was curious about as people start pondering questions they might have. So for the sun-like stars, where we have these granulation or supergranulation signals that last tens of hours to 20 hours, and they're kind of a pain to do from a single site, we've been thinking more about coordinated observing efforts and trying to hand off observations from one facility to another. Is there value to that type of approach, either for extending the baseline of like a dedicated high cadence effort on a single star, either for these ultra fast rotators that you mentioned, where you could catch full rotations of the star and really hammer on them over the course of 10, 20 hours? Or is that, because we don't worry about the granulation and supergranulation so much for M dwarfs, not an approach that you think would be a helpful addition?
Well, I'm never going to say no to more data. You're right that the granulation amplitudes are expected to be below, even the precisions that we can hit now with radial velocities. So I don't think that that's a motivating case. The ultra fast rotators is potentially interesting. So I mean, these signals seem to stay consistent for 6 months to a year. So it's not like you have to do this in a week. But I do think that if we detect candidates, I don't know if everybody will be convinced by my sine curve residual over 6 months. So it might be interesting if you have a candidate to do a dedicated, long-term stare where, yeah, you cover a rotation or a few rotations back to back, and you can see, nothing's moving over that amount of time. And if there's still something in the residuals, that might be neat for confirmation.
Other questions for Paul?
But I have a comment. There's on the RV content, you'd think that it's easy to predict how good an instrument will be at a given sonata noise within a band from the from models and so on. I've made predictions that were wrong, and others made predictions that were wrong. So I don't feel bad saying that others made bad predictions because we all made. In the NIRPS paper that François Bouchy's first author, we have a compilation of what we thought, what people claim would be for given spectral types and what we truly get. And actually things are a little better than anyone thought basically in the infrared. Not, I mean, the far red remains really, really important. I agree. So 800, 900 nanometers, so no doubt. But the ratio is a little bit, H band is a bit more exciting than what people would have thought, and Y band also.
Yeah, I agree that there's a lot of complexity to that discussion that I did not have time to cover. The main
I know
point,
it's a big mess.
of course, and the main point that I wanted to emphasize today is that we can do really well in the infrared. And yes, I think there's a lot more exciting stuff to come out of that. At the same time, these red optical instruments, if you look at Proxima and Barnard Star, NUID, Maroon X, Espresso can all do 10 to 50 centimeters precision on those targets, which if you put that together with infrared instruments and potentially the ability to discriminate from chromaticity, then I think that unlocks a lot of exciting possibilities.
There's one interesting point that you mentioned, and that's kind of emerging, is that M dwarf, they have personalities in terms of activity behavior. When we saw Andres Carmona's paper saying that flat line that you showed, and the other one, yeah, it's all clear. We recycled that one many times for proposals. And then Pierre Larue came and others came, and as you show a plot, some objects, they have exactly the same behavior. Others, they're just flat infrared. They really have personalities that we're just starting to understand. I think Pierre went some way in understanding why. It's not clear yet.
Right. So we saw, I'm going to back up a little bit. We saw this target right around the time that the AD Leo planet detection was published, and we thought, is there some class of planets that are all hanging out at the stellar rotation period? But yeah, I think it's just M dwarf personality, as you say.
Mm.
Okay, Chad, go right ahead.
So, Paul, I'm going to ask you what is probably an unfair question.
Love it.
So we've had HPF on Sky for something like 8 years now, and we have NERPS and SPIRU and a variety of visible light spectrographs and Carminas spanning the middle between them. So I'm wondering, since this was a very nice survey of a lot of the capabilities of different instruments, if you were to be starting over on the HPF project, if we were going to build another one today, what would you do differently in the instrument capabilities, in the design of the instrument, now that we know all of this that we didn't know in 2014?
Well, thanks for that nightmare fuel.
I try.
I'd have to think hard about that. Yeah, I mean, there are a lot of, little tweaks that would kind of have general improvements, but not really be a game changer.
Because I mean, I remember doing trades about, what wavelength regime do we want to go in based on activity and what resolution and concerns about, sensitivity versus breadth over larger numbers of targets and things like this.
Yeah, and that's the one thing I wish we had higher resolution. But that wish is tempered by wishing we had a bigger detector. We made a trade space between resolution and basically wavelength coverage on the detector, and I'm not regretting that choice. I wish we could have had both. I think that's where I would say, yeah.
So we need more work on bigger detectors that work in this wavelength regime and are suitable for spectroscopy.
Right. We don't need much.
Thanks.
Any other questions in the audience for Paul? Okay, well, if not, let's thank our speaker again. Thank you everybody for calling in today, and make sure to dial in again next month when we'll be hearing about NERPs from Etienne and Neil. Take care until then. Catch you guys in September.